Okay, so just a few review slides. This is one, actually it's available now under doc sharing, because yeah, there was 2 slides that you didn't have because it said from chapter 2. But I feel like I left you hanging a little bit because when we talked Monday or Friday, we had the Ptolemy model. Is the Ptolemy model right? No. Ptolemy still put the Earth at the center. Ptolemy still put the Earth at the center of the motion of the planets, like the planets orbit the Earth. Hello? The sun orbits the Earth, you know. And Ptolemy, do you remember what he did? I have a slide here to remind you. What he did was to make it complicated. And one of the hallmarks of science we're going to see here in a minute is Occam's Razor. And basically it says that if you're trying to take your observations and the more complicated you're trying to make, it's like playing Twister. You get all twisted up and you don't know what's what anymore. So the simpler model, the better. So this is the Ptolemy model. Okay, it puts you're showing, the orange here is showing a planet orbiting the Earth. You're like, dude, really? All right. So I left you hanging. Actually, if we step out of putting the Earth at the center of the planets orbiting the Earth and the sun orbiting the Earth, and instead put the Earth orbiting the sun and the other planets orbiting the sun, then actually we can finally account for that backwards motion called retrograde motion. So Copernicus, he wasn't the first one to come up with this idea. And I'll put the word up here. I'll try to put the word up here. It looks kind of, it's called helios. So one of the things, kind of the themes, I mentioned the whole church thing. The church really wanted the Earth to be at the middle of everything. Why? Because men are on the Earth and men are at the middle of everything. You know, there's still a lot of us that still believes that. I think nature's much bigger than man. But the other thing is that nature is perfect. Nature's perfect? Well, nature's pretty awesome, but nature's not perfect. And so if the perfect shape is a circle, which, okay, and so if nature is perfect and a circle is perfect, then nature must work in circles. Okay, I know it seems kind of illogical. And that includes, for Copernicus, that includes the path of the orbit of the planets. So he was close. Okay, I'm going to show you first how he could, with putting the sun at the center of the planets orbiting the sun, how could you explain the fact, and I'm going to try to show you on a sky map, how could you explain the fact that sometimes it looks like the planets are going backwards against the background stars? Well, at the crux of this, I'm going to show you, and I'm going to show you a figure, and I'm going to show you a sky map, is the fact that planets that are on an inner track, planets that are closest to the sun, move fastest relative to planets on our outside track. Okay. So with that in mind then, as a planet on an inside track comes up against a planet on an outside track that's moving slower, as it approaches it, it looks like the planet's going backwards. So I think a really good way to... Yeah.
Are planets closer to the sun actually moving faster, or they're just covering less distance?
They are covering less distance and moving faster. Yeah, that's a good point. They're doing both. If you drive much, you probably felt this very same sensation. So let's say you're a fast driver, okay? And let's say you go in the left lane a lot. And so in this scenario, you have a car you're coming up on in the right lane, you're in the left lane, and let's just go ahead and make a grove of trees in the background. Okay, that's actually going to be our background stars. So here we go. So you're going faster, okay, and they're going slower. So as you approach the vehicle that's going slower, okay, that vehicle, if you were to look against the background, the trees, that vehicle still looks like it's moving this way. This way. Okay? Now, a sensation happens as you kind of come upon it. Okay, it's going this way, and can you see as I'm getting near it, it finally looks, when I'm in the vicinity, going to overpass it, it looks like it's going backwards, okay, relative to the background. I go ahead and pass it, okay, and then it appears to go forward again. It's a sensation. If you passed cars, you've seen it all the time, felt it all the time. Just for that moment of coming up on it and passing passing it again. Okay, then it goes forward. So let me go ahead and show you this. I have a figure from your textbook. I think you still have this figure in your textbook. You have a similar figure in your textbook. Oh yeah. And it will show you what color. If you were gonna depict the Earth, what color would you depict it? If you're gonna pick Mars, what color would you depict it? There you go. Quite clever. Okay. So here you see 7 positions of the Earth and Mars. And then the way this works is you can see where Mars is against the background constellations. At position 1, it's in Gemini. Okay. Notice that we would expect kind of retrograde motion to happen kind of here, 3, 4, and 5, based upon what I said. Okay, so this should be direct motion. Okay, and again, this doesn't happen in one night, over the course of several nights. Okay, it's moving now to a constellation eastward. Okay, position 3, it's still moving eastward, 1, 2, 3, eastward. We call that direct motion. Okay, and then finally, I'll just go ahead and do this whole thing. Then finally, at position 5, 6, and 7, it's going direct again. 5, 6, 7. So the way this works is, this is direct, and this, the 3, 4, and 5 was retrograde. Okay, and according to Ptolemy, that planet was orbiting the Earth. And in retrograde, it just kind of had a little loop-de-loop. We call an epicycle. Okay. So it's interesting. The wanderers, right? So I mentioned that I went to an astrology site to find out when retrograde motion was going to happen. And on that example, and you can go back and prove it if you want, but there about, at the end of September, the beginning of October was when we saw Mercury kind of doing its backwards, okay, and that starts retrograde motion. So again, astrology is not a science; it's not provable. Okay, there's some hallmarks of being a science that astrology fails. Okay, but it's great for keeping track of some of these celestial events. Okay, so changing gears a little bit. I think I mentioned this before that you're going to see Galileo was up against this. The problem with putting the sun at the center of our solar system and having the Earth move around the sun is that as something moves, like I'm going to kind of show you this guy and this gal, if something moves or from a different perspective, how do we say, things kind of scramble their position. It's called parallax. And it only happens, or it happens when there's a close object like this tree, and there's a faraway object like that mountain. So here you go, parallax. So can you see where this guy looking at this treetop sees it right over here? Okay, the trajectory, right? Well, where's this girl going to see that treetop? Over here. Okay, same treetop, tree's relatively close. Okay. The mountains are far away. Someone reminded me, and this is, I've heard this too, and don't be embarrassed if you're going to right now. So you put something near your face, like your finger, okay, and then to get a different view of your finger, you close one eye and the other eye, and you see where it is. Against, I'm looking like at that window, and right now it's over there, or there it's over there, depending upon what eye I look at. Parallax.
So, and if you do it really fast, you can play mind games.
Yeah, it's like, oh, I agree. So if the Earth was moving in space, then kind of, if the stars are kind of close by and the Earth is moving, then we're going to see different sets of constellations as the Earth moves in space. Okay, parallax. So that's one of the things that we're going to see that Galileo had an answer for. He has an answer for everything. No, he doesn't. but he was up against. So this is after Galileo's time, and actually this is after we're going to talk about Tycho Brahe, and Tycho Brahe had an awesome telescope. But we do see wiggle in stars, in the location of stars. If, like that tree, if a star is kind of nearby, when we are at different positions from the sun, like at January and July, we're going to see that star at different locations if that star is relatively close. So in this example, yellow star, relatively close. Pattern of white stars, far away. So here's the deal. In July, we see that relatively nearby star kind of over here on the edge of that pattern of stars. Where do you think we're going to see it in January? Trajectory, yep, on the other side, exactly. That kind of wiggle in the location of a star as we change our position in space, because we're orbiting the sun, that's called parallax. And actually, we can use that wiggle to determine how far that star is. We can use that angle, parallax angle. So we do see parallax. They just didn't see it in their time. So I mentioned Brahe has this awesome telescope. Okay, Tycho Brahe. He's the, I don't know if he was really like this, but in my own mind, he was kind of like a spoiled brat who had all sorts of money. And I think like he fought a duel, and he's the dude that like has half of his nose missing. Yeah, he's famous for lots of things. But this is his toy, or a picture drawing of one of his toys. So he had an awesome telescope, but he needed a little bit of help. Even going with Copernicus' idea of having a heliocentric model of the universe, you know, the Earth orbiting the sun, the planets orbiting the sun, even in that case, he still could not predict where the planets would be. Okay? He just couldn't. And also, you see parallax. He's like, dude, I have looked at those patterns of stars till I'm blue in the face, and none of them move. They are like cemented. He didn't see what we saw a minute ago with the yellow star kind of moving against background stars. So no parallax. You know, I'm still having a hard time predicting where the planets are going to be using a circular orbit. So if he's like a spoiled brat, which I don't know if he really is, then to the rescue is Kepler, Johannes Kepler. So not quite so rich, but great with thinking through things. Okay, so Kepler. So Kepler tried to stick with the, the perfect shape of a circle, but he's like, dude, I cannot take your observations and predict where the planets are going to be based upon them taking a circular shape. But I can if I take that circle and make it into an oval. Another name for an oval is an ellipse. Ellipse and oval is the same thing. So it's like, dude, look at your data again. Okay, we all need scientists like that are going to kind of take the next leap, and that's what Kepler did. So he tried to ignore the kind of little offish using circular orbits, but finally he's like, let's just throw that out and go with something that's not perfect, an ellipse. Although ellipses are pretty darn cool. Okay, so actually, kind of you see from left to right, you see a circle and an oval, a circle and an ellipse. Okay, actually a circle is a special type of ellipse. So you kind of see some features of ellipses listed down here. Ellipses have what I call two belly buttons, okay? And I know they're not really belly buttons, but they're called foci, and there's special spots in an ellipse or an oval that you can, like you see this yellow string, kind of put thumbtacks there and take the yellow string like a spirograph, go around and make your ellipse with your two belly buttons there. So the thing with a circle is the two foci overlap. So what else do we have with an oval or an ellipse? Well, we have a center, like you see here, okay, and then through the center you see the crosshairs. The short crosshairs is the minor axis, and the long crosshairs is the major axis. Makes sense? The one last thing about ellipses, and we're going to talk about ellipses again when we talk about galaxies, the shapes of galaxies. But they have a degree of ovalness. And we call that eccentricity. So eccentricity can vary from a value of 1 to 0. An eccentricity of 1 is there's no ovalness. It's a circle. Their foci overlap. Eccentricity, did I say 0? Eccentricity of 0. Okay, no ovalness. Okay, and then it approaches the value of 1, moderately eccentric, and then highly eccentric. So you just see it getting more and more oval. So 0 is no eccentricity. Okay. So actually then, that is Kepler's first of 3 laws. There are 3 laws that Kepler came up with. They're not theories, they're laws. There's a subtle difference. Okay? Based upon his observation of the motion of the planets, there are 3 laws. And actually, this is consistent with one of the things we talked about before. We said that they're about January, see, how do I put it over here? See, yeah, thank you, January 3rd, perfect. And July 3rd? Yeah, July 3rd-ish or so. We said that sometimes the Earth is closer to the Sun and sometimes the Earth is farther away from the Sun. Okay, perihelion, aphelion. And so that makes sense if the Sun is off-center at one of those 2 foci. Okay, and all of the planets, let's see if I can draw one a little bit larger. So that's the Earth. This would be Mars. And I'll draw one inner. And this would be Venus, okay, Mercury, you get the idea. They all are ellipses, and they all share the common foci, the Sun being one foci. Now, if you're like me, you want to go visit the other foci. It's nothing lies at this foci. I'm telling you, somebody needs to write a science fiction movie with the storyline. That, you know, it's a thought. Or not. Okay. So the terms perihelion and aphelion can apply towards any of the planets. Next. Okay. So that was his first law, the shape of the orbits of the planets. Again, kind of segueing from circle to an ellipse, or an oval. His second law goes like this. Let's see if I have all this up here. His second law says that equal areas will be swept out by equal times. And in order for this to make sense, you have to recognize, again, those important points, perihelion and aphelion. And for this to work, actually, the planet needs to go fastest. Okay. So I get to make sound again. If you've had me for another class, we'll talk about something called the Doppler Effect. And the thing is if the sound is something, if the pitch goes up, that means it's going faster, and if the pitch goes down, it means it's going slower. So here's the deal: at perihelion, a planet will move faster, and slowest out here at aphelion. So it goes, and it's all about counterclockwise. Can you see that looking down counterclockwise? Okay. It goes. It's kind of like one of those Adventureland rides. I know. Right. So here's how this works then. Oh, it didn't. See, my builds aren't working. All you heard was the sound. Well, that's no fun. But I don't know why my builds aren't working. Well, that one worked. right? Right? Okay. That's what I was trying to say. And then to kind of clean that, I'll clean up the slide. Here's how this works. If we go ahead and mark this as segment A, oops, let's go this way. A, because it's going counterclockwise. A and B, okay, time segment-wise. And we'll mark this one over here, C and D, time segment-wise, okay. The time that it takes for a planet to go from A to B is the same as it goes to C to D. The time. And I don't know if that's, 5 days, because it's going faster at perihelion. So then in his law, the areas part, can you guys see a triangle here? With kind of a curved end, okay? The equal areas goes like that. That area is equal to this area. That's it. Equal areas, equal times. And I like what I have at the bottom of this slide. So his whole equal areas things, the only way it can work, because you're making a triangle back to the sun, at the vertex. The only way it'll work is if you're going faster at perihelion than you are at aphelion. That's the only way it'll work. So that's important. Okay, his third law, and we do this all the time in physical science. I worked at a coal research facility run by the Department of Energy in Morgantown, West Virginia for a year. And what they did, what that guy did, that scientist did, I was like his lackey. And we just looked at coal, and we took all different parameters of coal and looked for things that were linked with a particular coal. So anyway, for a particular planet, if you take that planet's, how long it takes to orbit the sun, its orbital period, and if you take the average distance from the sun in astronomical units, AUs, they have the relationship of being squared and cubed respectively. Okay, so P squared is equal to A cubed for a given planet. Okay, so the period is related to the distance.
So what was that before? The P equals the orbital and the A equals the AU?
Right. The P is equal to the time it takes to orbit the sun, orbital period in years, and the A is equal to its average distance in astronomical units. So when anybody now talks about how far away is a planet from the sun, you have to maybe start kind of thinking, well, is it at perihelion or aphelion, right? Because all planets are sometimes closer and sometimes further from the sun. So the whole thing with average is it probably involves calculus, I don't know, coming with the average distance. Okay, so, and it kind of makes sense, okay? Come on. All right. So here, side by side, for each planet is how long it takes to orbit the sun, which is kind of fun. How long does it in years? The Earth is 1 year, makes sense, 365 and 4 days. Okay, look how long it takes Pluto to complete one cycle around the sun. 248 years, Earth years. That's a long time. And the average distances in astronomical units. So if you square this column, you get this. And if you cube this column, you get this. So then the coup de grace would be how well do they agree with each other. Not bad. That's Kepler's third law. See what I mean? I think he was kind of smart. So it takes a village to raise a science. I just made that up. So I don't have anything necessarily to show you here. I think these are available to you if you have Mastering Astronomy. All right. On to another guy. This is actually kind of wrapping up the history part. Okay, Galileo. And one of the things that comes to mind is you kind of picture Galileo with a telescope. He didn't invent the telescope, but he was the first one to look at celestial objects. I'm glad he didn't go blind because he saw sunspots on the sun. Anyway, so Copernicus, so Galileo agreed with Copernicus, the heliocentric model, the fact that the planets and the Earth orbit the sun. He's like, I'm so in with that. But things that he made progress in making sense of, or things that people were still hung up on. Check this out. I like this. If the Earth is moving, okay, orbiting the sun, then as it moves, it's going to leave its air behind. Isn't that funny? I know, it's, yeah. That was one of the objections that he's like, hey, it's okay. And so he actually, and it makes sense because, like, I mean, I think this is what they were. For instance, if I take something flat, okay, and what's going to happen to this pen if I move this black thing quickly? It's going to fall off. Yeah. So, that's what I think they were afraid of, right? Okay. But basically, he kind of, I think it's kind of cool, is Galileo got ahead of where Newton eventually went. And basically, he said, he proved that if the air is already in motion with the planet, okay, that air is going to stay in motion with that planet unless acted upon by an outside source. So it's here to stay. Okay, it's already in motion. Then the other thing is the whole circle thing, a little bit the circle thing, but just in general, yeah, the circle thing. And the way he came about kind of saying, dude, go with an ellipse, you're fine, is he pointed out other imperfections in nature. He's like, look, you think that's bad, nature is not perfect. And the other thing is he basically put into perspective why, if we are in motion, why don't we see parallax with stars? Okay, why don't we see different patterns in the sky? So this was the air would leave the Earth, okay, if the Earth were moving, okay. So the way this works is if I were to do this little experiment, and this must have been what he did, I didn't look into it, but basically if instead of doing this, if I were to go ahead and do this, okay, right now, the difference there is right now my pen has the motion of my plate, okay. If I do it quickly, I don't give it enough time to get that motion. Okay, so he kind of did what Newton ultimately did later. So the whole thing about get over the ellipse, it's here to stay, Circles are great, but nature does what nature's going to do. Okay, he actually, not Galileo, but Tycho, the one with the cool observatory, what Tycho saw was a supernova event. We're going to talk more about those. You're probably familiar with a star blowing up, supernova, a star blowing up, and that you're definitely on the right track. So the fact that that the heavens aren't perfect, basically when a star goes supernova, you see a normal star, okay, and then basically you see an explosive event, the remnants, the guts of the star, and it's there for maybe a couple weeks. And then what do you think after that dies down? What do you see? Nothing. That's right. So you kind of let nature be nature. The other thing is he used his telescope and he saw that the sun is not perfect. Okay, none of us are perfect. The sun's not perfect. It's got these little blemishes on it. And then he also saw that the moon's not perfect. It's beautiful, but it's not perfect. Okay, it's not homogeneous, same throughout. All right. So then about the whole parallax thing, and can you imagine, I wonder if before Galileo, because he published, right? Galileo published. He put out a paper, which was a big whole hairy deal back then. It's not like they had the internet, right? But anyway, even before Galileo, I can imagine like sailors taking their telescopes and looking at that thing we call the Milky Way. Okay. And I'm telling you, we all should do that, okay? Because what looks like little dust, basically, are stars. And so he basically said, all right, if everything's far away, you don't see parallax. So an example of that, then, if you picture the woman and the man kind of looking at the nearby tree, okay, and it looks like it's different against the background mountains, take a tree, or take that tree if you want to, and put it on the mountain. Okay, And then go ahead and be the guy, and be the woman. You'd be like, okay, so if the tree is on the mountain, you don't see any parallax because it's so far away. And that was his point. Okay, very far away these stars are. All right, so another thing that Galileo saw was the circle there is Jupiter. The little stars there, he saw that these objects were orbiting Jupiter. These are 4 of Jupiter's largest. There's 4 down here. These are, there's 4 here. There's not always, you can't always see 4. Why can't you always see 4, you think? Are there times when?
Because there's some behind it.
Some behind it, exactly. But he observed this and he wrote it down and he's like, dude, this is a pattern. Okay? We call these the Galilean moons of Jupiter. Isn't that cool? It's like poetic. Okay. Another thing he saw was if you look at the planet Venus, now the thing that's different between Venus and Jupiter, there's a lot of things different between Venus and Jupiter, but one of the things is that Venus is on an inside track. So Venus being on an inside track, it gives us the possibility, or we will see Venus go through phases, just like, don't these look like phases of the moon? We'd call that full, gibbous, quarter, crescent, kind of from right back to left. We see these phases of the moon, we see these phases of the planet Venus because, like, for instance, when it's here, we don't see it, right? Oh, a really cool thing that happens sometimes is Venus will go in front of the disk of the sun. It's called a transit. It's really cool. Kind of rare because, it kind of bobs up and down. And then we see a crescent and we see a quarter, gibbous. Do you think we'll see Venus over here in its full stage? Probably not. Too close to the sun. Okay. But if you compare that to, this is what Ptolemy thought. Compare these two. It puts the sun at the center. Venus and Earth is okay. This is what Ptolemy thought. Ptolemy thought that Venus orbited the Earth, the sun orbited the Earth, and Venus did these little epicycles. There's no way, if you put Venus between the Earth and the sun, that you're going to get the phases that he saw. You get phases with the heliocentric model, but not with the geocentric model. Smart guy. So there are books out there on Galileo, and it's kind of a sad story. I mean, as brilliant, as much fun as I imagine he had with his findings and sharings and all that. Remember I said that Copernicus was kind of, Copernicus was kind of careful when he published, not to step on too many toes. Well, the church actually, and he was like a staunch Catholic, and the church gave him a really hard time. House arrest, and so I think he died under house arrest. But his daughter was there by his side, and it's just kind of one of those stories. In 1992, they vindicated him. Okay. So just a few slides to kind of wrap up just science in general. So that's all the history. They have to think about this. Science comes from knowledge, but not all knowledge is science. What's that? But I was kind of thinking, for instance, history. We are so lucky to have the history teacher we have here on campus right now, Mr. Evans. But anyway, history is full of facts. Indisputable facts, well, and sometimes I think in history, depends upon who you listen to, I guess, right? Okay, but that's knowledge. But that is not a science. I would say the difference between social stuff, that stuff that people do, and science is predictable. I love science. Science has a personality, but you know what he or she's generally going to do. So, just a few terms you're probably familiar with. The term hypothesis is kind of early on in the scientific method of ultimately developing a theory. Okay, hypothesis is basically you have made some observations, okay, based upon what you saw, you're like, hey, well, I think maybe this is how it works. Okay, that would be your initial or your best guess. So then what you got to do is to design an experiment to test if you're right. So you take your hypotheses, you make a prediction, then you design an experiment. You can kind of see this whole left-right sort of thing. Okay, so what the left arrow tells us is that your experiment fails. It happens. You know, I tell people in the chemistry lab, be proud of your data. Doesn't make sense, be proud of your data. Okay? But in the scientific method, if your prediction doesn't come true, okay, you can maybe, and you can look at your experiment, design a different experiment, or adjust your hypothesis, or throw it all out. Change your career. Okay? But if your prediction is correct, okay, you're not done. If your tests say, yeah, you were right, well, you got to do more tests. Okay? More and more and more and more. And not just you, but everybody else in the world, okay, does this a lot. Okay? I say that scientists are like little kids where they, a lot of times at their hearts, want to prove the other guy's wrong. Okay, so you'll have your sector of science and everybody's like going at it. Now, after doing this a lot, okay, then if you continue, if your predictions continue to be right and your hypothesis continues to be validated, then you can go ahead and elevate your hypothesis to a theory. And this is my own device, I think. I liken it kind of to if you're playing checkers and you fight and you fight and you fight with your opponent and you get to their side, okay, what do they do when you get over there? Yeah, they king you, exactly. It's like, ta-da! That's what a theory is. A hypothesis became a theory. Like a bill became a law. Okay, so these kind of make sense. One of the things about science, I said we kind of remove the emotional side. Okay, we remove the mysticism. Quite frankly, we remove the religion part from science. Okay, and natural causes are the crux of why things happen. Remember when I said Ptolemy came up with a model and he introduced of how planets can have that background motion? If we go ahead and have planets orbiting the Earth and have little epicycles, too complicated. Okay, and it's called Occam's Razor and can be abbreviated KISS. What's that stand for? Keep it simple, stupid. Yeah. You know, it's like, the more complicated it gets, it's like, dude, you're making it too complicated. Let's go back to the basics. And then the last one, and this was an important part of the scientific method of taking a hypothesis and elevating a hypothesis to a theory, is you need to be able to test it. If you can't test it, it's not a science. Okay? So this is my little stab at a little bit, or just a reminder then. If somebody says it's just a theory, I'm probably guilty of it too. Just a theory, if that theory has survived the board and gone over to your opponent's side, started as a hypothesis, that's no small feat. So theories are supported by the body of evidence. They are, the scientists in general think it to be the case. Okay. Any questions about that? Okay, 1 minute over, but not bad. So this will be due then when we meet again.